This video is about servomotor position control. Exactly what that means will be discussed first. This is the mechanical unit. That's the servomotor axis. The goal is position control of this axis, the output shaft, which is connected to the servomotor through belts and pulleys. This block diagram shows the most significant components. That's the servomotor. That's the potentiometer that measures the position of the output shaft. The output signal in volts is the potentiometer voltage. The desired position in volts is a triangle or square wave reference signal. The error signal is the difference between these two. An error signal of 0 means that the desired position is equal to the output position. In other words, the output position will be following or tracking the input signal when the error signal is 0. The PID controller modifies or manipulates the error signal. And individual effects of P and I and D on position control is the main focus of the video. ESPIAL, practical number 2, three-term position control. This is the first PID control of position. This is the system block diagram. That's the set value signal. That's the error signal and the control signal and the measured value signal or the response signal. Initial setup instructions. All signals are 0 because the output amplitude is minimum. Increase the input signal amplitude, which is a triangle signal, but with only proportional control initially. As the proportional control is gradually increased, all three signals show up. That's the input signal is blue, the response signal is yellow. Ideally, the yellow signal would track the blue signal. Set the input signal period to about 6 seconds. Click on the capture button. Click on the main cursor button and click the first cursor. Click on the delta cursor to click the second cursor position, which will then read the period of 6.33 seconds. Change the proportional gain and note that decreasing the gain increases the following error and increasing the gain decreases the following error. Currently, the proportional gain is 50%. Now the proportional gain is 25%. Now the proportional gain is returned to 50%. And now the proportional gain is set to 100%. The proportional gain is returned to 50%. Did you notice that increasing the proportional gain caused the tracking error to decrease, and that decreasing the proportional gain caused the tracking error to increase? That's when the proportional gain was 50%. That's the tracking error. When the proportional gain is 25%,
the tracking error is larger. When the proportional gain was 100%, the tracking error was smaller. Replace the triangle wave with a square wave input. The proportional gain is 100%, produces a large overshoot. When the proportional gain is 25%, there's no overshoot, but the response is sluggish. Proportional gain is 100%, and the derivative gain is turned on now to 65%. The overshoot is almost zero. Return to the triangle input, the proportional gain is 100% and the derivative gain is 65%. Note the following or tracking error. Turn the integrator on now. With a gain of about 25%, note the following or tracking error goes to zero. But 25% integrator gain increases overshoot. In summary, proportional gain decreased the steady state tracking error, but increased the overshoot. Adding derivative gain decreased the overshoot, but did not decrease the tracking error. Adding integral gain decreased the tracking error, but increased the overshoot. Unfortunately, these three gains, proportional, integral, and derivative, create effects that are not independent.